Hey everyone, I'm going to go through the second part of the 16.6 notes with you if you want to watch this. We're going to talk about how we can do a couple things with our parametric surfaces. So, yesterday we talked about parameterizing some of these surfaces. Today we're going to talk about, first of all, tangent planes. We've done these a bunch. I'm sure you will be well versed in them, but we're going to see how this is going to help us today. We're going to find the tangent plane to a parametric surface traced out by some vector function r, as we saw yesterday, which is dependent on two variables u and v at some point, so that we have our point P, which has a position vector pointing at it, by plugging in that u naught and v naught. If we keep u constant by setting u equal to u naught, then r is just a function of v. And it defines a grid curve, which we talked about yesterday. Lying on S, the tangent vector to this grid curve at that point is obtained by taking the partial derivative of r with respect to v. So you'll notice our notation here, r sub v. So u is fixed. We take the derivative with respect to v. Alternatively, if we keep v constant by setting that equal to v naught, then r becomes a function of just u and defines a second grid curve, a different grid curve lying on S. Tangent vector to that grid curve at that point P naught is going to be obtained by taking the partial derivative with respect to u. You see that notation right there. So taking a look down here at our visual, you will see our two lines where we're holding u fixed, and then where we're holding v fixed. You can see our point P naught right there. And those are corresponding to our curves over here. Sorry about that. So we got a curve right here in blue that I'll draw. No, I think I got that backwards. I think that is supposed to be C1, which is that way. Red holding V fixed gives us that curve right there. And you'll notice our two tangent vectors to the curve. So we have oh, you know what? That says RU. You know what? No, never mind. I'm good. I don't know what I'm talking about. R sub u, that is where V is fixed, because we're having a function of u. My bad, my bad. So we have our tangent vector right there at point P naught, and then when u is fixed and we take the partial with respect to v, there's our tangent vector right there. And have a vocabulary word for you right here. If we cross r sub u and r sub v, those partials, and if that is never the zero vector, notice that that is a vector, then the surface is called smooth, meaning it has no corners. For a smooth surface, the tangent plane is the plane that contains the tangent vectors r sub u and r sub v, and the vector r sub u cross r sub v is the normal vector. If you remember doing those things, that is going to be that vector that helps us define the equation of our tangent plane. So let's take a look at a weird surface right here. We're going to find the tangent plane to the surface with parametric equations x equals u squared, y equals v squared, and z equals u plus 2v at the point 1, 1, 3. You'll notice this is one of those planes where it's self-intersecting, kind of crosses over itself. So, how are we going to find the tangent plane? We need a normal vector for a tangent plane at a point. So we have a point, we need the normal vector, and how we're going to get the normal vector is crossing the partial of r with respect to u with the partial of r with respect to v. Excuse me. So we need that vector r sub u, which is going to be equal to the partial of x with respect to u, partial of y with respect to u, partial of z with respect to u, which in this case, looking at our three components, that is going to be 2u, 0, and 1. Sorry, some of my u's are looking a little sloppy. Our other vector, r sub v, is the partial of x with respect to v, partial of y with respect to v, and the partial of z with respect to v. Looking at my three components again, that is going to be the vector 0, 2v, and 2. Now, to get the normal vector, we have to cross those, bringing back our cross product using our determinant of a 3 by 3 matrix. Right there, so we're going to get 0 minus 2v, so that's just 2v. I'm going to do this backwards so that I don't have to negate it, so I'm going to do 0 times 1 minus 2u times 2, so we're going to get minus 4u. And then for the last one, we're going to get 4uv minus 0, so that is 4uv. So there is our cross product. We are doing this at the point 113. Now those are values for x, y, and z. And you'll notice that if we're going to use this cross product vector, we need values of u and v, not x, not y, not z necessarily. You'll note that this corresponds to u equals 1 and v equals 1. It's a nice point for us to use. So our normal vector, I'm going to take that cross product vector right there, and I'm just going to plug in 1 in for u and for v. So we get negative 2, negative 4, and 4, which you could simplify if you'd like to negative 1, negative 2, 2, or 1, 2, negative 2, a couple different ways to write that. And you'll hopefully recall from earlier in the year our tangent plane equation. We're going to take those three values in the I, J, and K spots right there. Those are going to be our coefficients, our slopes, if you were, of the x, y, and z. And then we just need to do that kind of point slope thing where we're going to subtract from x, y, and z the coordinates of the point that we're doing this at. So that would be negative 1 times x minus 1. That's right there, and that is right there. Minus 2 times y minus 1 plus 2z minus 3 equals 0. Doing a little bit of rearranging here, we get negative x minus 2y plus 2z, 2, so that's 3 minus 6 is negative 3, moving that to the other side, or I guess you can keep it on the same side, equals 0 like that. You can move things over a couple different ways to write that, but there is the equation of our tangent plane. I'm going to stop this half of the video right here before we talk about surface area. So that'll be a reminder of tangent planes, and this is how we're going to get them using our parametric surfaces.